This is part 2 of Unit 2 GCSE Chemistry for AQA. Specification, first part about molecules and ionic compounds, and also about covalent structures. Here are the key things to understand this part of the unit. It's all about the physical and chemical properties and their strong influence by the structure. We know that structure we can predict some of the properties. Structure is so important that even the same element has different properties according to its structure, and we'll see that later on in carbon. If a substance is made up of molecules, it's usually a gas, liquid, or a low melting point solid. It's an insulator. This is because it'll be non-metals and they don't conduct electricity, and also non-metals do not have any free or delocalized electrons. Key feature of molecules are their low melting and low boiling points. Property of ionic compounds. This is the ionic compounds we saw in the last presentation, are formed by metals and non-metals. They have strong electrostatic force in every direction in the lattice, and these need energy to be broken down in order to melt or boil. So ionic compounds have a really high melting point, example in thousands of degrees C, to try and split this lattice up. Ionic compounds readily dissolve in water. Here's the example of sodium chloride, which is common salt. As you know, sodium chloride, common salt, is easily dissolved in water, and when it does, it forms the sodium and the chloride ions float around in the water. To conduct electricity, there must be charged particles that are able to move, and therefore solid ionic compounds cannot conduct electricity because the ions cannot move through the solid lattice. However, if you melt them and turn them into liquid compounds, molten, then they have ions which are free to move. The other way to conduct electricity is dissolve it in the solution. For example, water, salt in water, brine, if you like, will have ions in it which are free to move and therefore can conduct electricity. Here are some typical covalent molecules. Hydrogen, oxygen, nitrogen, chlorine all exist as gases. H2O2, N2 and Cl2 means that they need two atoms of each element to be bonded together. Covalent bonding means to share the electrons. And a few other at the bottom then of different elements: nitrogen oxide, water, nitrogen dioxide and carbon dioxide shows the covalent bonds. And now we're going to look at how we can break the intermolecular bonds. That's the bonds between the molecules. And now we're going to look at how the structure of molecules can help explain their properties. When the molecular substance melts or boils, the covalent bonds don't break. These are very strong. However, the molecules are relatively easy to separate from one another. We say that the intermolecular forces, or forces between the molecules themselves, are very weak. The size of the forces relate to the energy needed to break them, and therefore very weak forces equals very low energy, which equals very low temperatures. So most covalent molecules exist as gases because they have very weak forces between the molecules themselves. If we look at the properties of giant covalent structures, well, they have the opposite. They have very, very high melting points and very high boiling points because you need to break the covalent bonds. So diamond, graphite, glass do not easily melt at all. Diamond is very hard, as you know. These giant molecules are sometimes known as macromolecules. You may remember from the first presentation that graphite is pure carbon. Carbon bound together by three other carbons, a very, very strong bond between those, very hard to break. However, the fourth bond is very, very weak between the layers. This gives graphite quite unique properties. So graphite between the layers can rub away so soft, unlike diamond. Remember, diamond being pure carbon too, but with four bonds between the carbons. So graphite has a very high melting point because of strong covalent bonds, but it will conduct electricity because between the layers you get delocalized or free electrons to carry the charge. In this way, it's very similar to a metal. We now look at fullerenes. You know the element carbon can exist in different structural forms, which are known as allotropes. So the two common allotropes of carbon we've looked at are diamond, a very hard structure, and graphite, quite a soft structure because of the way they're bonding. Carbon can also exist in other forms, collectively called fullerenes. Now the first of these, Buckminster fullerene, was discovered by accident in 1985. And its discovery opened up into a whole new area of chemistry. You can see the complex structure there, composed of 60 carbon atoms. So we call it C60. The physical properties of Buckminster fullerene are that it is a black solid at room temperature, which does not conduct electricity. It's insoluble in water but dissolves in petrol to form a deep red solution. Its molecules are strong and hard, but elastic like a football. They can be squashed to 70% of their normal size, but will bounce back. The molecules can be used as a cage to trap atoms and smaller molecules inside of them. The surface of C60 molecules can be coated with other atoms. For example, coating with hydrogen makes a very smooth substance that is even more slippery than Teflon. The molecules can be joined together to make bigger fullerene structures. C60 molecules are also known as buckyballs, and since the discovery of this first fullerene, other types of fullerenes that have been made include the C70, made up of 70 carbons, which are shaped like a rugby ball, bucky babies with less than 60 carbon atoms, fuzzy balls with coated with hydrogen, and giant fullerenes with much more than 60 carbon atoms. You don't need to know details of fullerenes, just that many different types exist. You do need to know some uses of the fullerenes. For example, non-stick slippery coatings for machinery which act like miniature ball bearings, cages to hold drug molecules that can be delivered directly into the body, molecular sieves which trap large particles like viruses while allowing smaller, healthy particles to pass through, and chemical sponges to soak up toxic substances in the body. The main uses of fullerenes, to remember, are drug delivery, lubricants, catalysts, and reinforcing materials, for example nanotubes in tennis rackets.